Hi, welcome back. In this video, we're going to introduce one of the core elements of the course, the How to Design Functions design process. A design process is a set of step-by-step instructions for solving design problems. We say that design processes support systematic design because of the way they help us solve any problem in a regular or systematic way. In this sense, design processes are kind of like cooking recipes, so we sometimes also call them design recipes. We'll be using the How to Design Functions recipe, or HTTF recipe, throughout the course. Before we start, a couple points to keep in mind. At first, the How to Design Functions recipe will seem like overkill. The function we design in this video is simple enough that you are likely to think that we don't need so much process to design it. And you'd be right. But before long, the recipe will be enabling you to design functions that are more complex than you could manage without using a design process or a systematic design method. So please be patient with this aspect of what systematic design processes do. They do make very simple problems more cumbersome, but in exchange, they make hard problems possible. So use these very simple examples now to learn the design recipe, and then the recipe will pay you back later, helping you solve much harder problems. A second point of introduction is that we're going to start by just going through an example of using the recipe fairly quickly to give you an overview of the whole process. The first time we go through it, try to just sit back and observe the overall structure of how we proceed. Don't try to absorb all the details of what is happening, and don't worry about being able to reproduce the recipe yourself after just watching this first time through. You can always rewind the video, and more importantly, lecture and other videos will go through the HTTF recipe again in more detail. We'll go through this design recipe hundreds of times in the course, and each time we'll introduce a new aspect about how it can help us solve a hard problem. So here we go. The problem that we're being asked to solve is to design a function called times2 that consumes a number and produces the given number times 2. So for example, times 2 of 3 should produce 6. Now this problem statement very clearly says that we're supposed to design a function. So the How to Design Functions recipe is the tool that we're going to want to use. Now, if we go to the course website, here's the course homepage, and we look under Design Recipes, the first of the design recipes is the How to Design Functions recipe. HTD stands for How to Design. So we can go to the How to Design Functions recipe, and what we'll see on this page is a short summary of the recipe as well as a detailed explanation of using it to design times2. We won't go through that detailed explanation now, but you should review it at the end of the video. Instead, we'll use, and you'll use this throughout the term, this short summary of the recipe, which lists the individual steps. So let's get going. The first step is called signature, purpose, and stub. So let's go back over here to Dr. Racket, where I have a comment box with the problem statement in it. And what I'm going to do first is save this in a new file, because it's a good idea to always save your work quite often. So we'll save this in a file called times2. Okay, so the first step of the design recipe is to do something called the signature. The way we write the signature, in this case, is we put 2 semicolons, and then we'll put number, and we'll make an arrow with a dash and a greater than sign, and write number again. And the way we're going to read this is that this function consumes a single argument of type number, and it produces a result of type number. And notice that we're writing these types with an uppercase initial letter. That's going to be how we write types throughout the term. So this signature tells us that the function we're designing consumes a number and produces a number. The second step of the recipe is the purpose. I'll put 2 semicolons and a space, and I'll write produce a number that is 2 times the given number. The purpose is a short, less than 72 characters, description of what the function produces that tells us more detail about what it produces than the signature does. The signature told us that it was a number. Here we know that it's a number that is twice the given number. So the purpose always tells us a little bit more detail about what the function produces in terms of the argument it received. So now we have the signature and the purpose. The next step is to write something called the stub. Let me just write it first and then talk about it. Well, it's a function definition. We say define the name of the function, some argument. And what the stub has to do is we want the stub to be the simplest function we could possibly write that produces a result of the correct type. It has the correct function name times 2. It has the parameter, and it produces a result that's a number. And this result isn't going to be right very often. In this case, it'll only be right if we call times 2 with 0 as an argument. It doesn't need to be right very often. Its only job is to have the correct name, correct number of arguments, and produce a result of the correct type. We're going to see a lot more about how stubs are going to help us as we go into future examples. So for now, I'm just going to go on having written this stub. So the first step was the signature, then the purpose, now the stub. Now we're going to write what are called examples. And Dr. Rackett gives us a very nice way to write examples by saying we write check expect, and then we write an example of calling the function. For example, if I write times 2 of 3, then what do we expect that to produce? Well, we expect that to produce 6. And if I wanted to write another example, I could say check expect times 2 of 5, and what would we expect that to produce? Well, that's going to produce 10. So the way you read check expects is you say, I expect that if I call times 2 with 3, I'm going to get 6. And I expect if I call times 2 with 5, I'm going to get 10. And what we'll see in a minute is the reason it's called check expect is that once we're done our design, we can get Rackett to check these examples for us automatically and tell us if our function is producing what we expected it to. So now we have the signature, the purpose, the stub, and the examples. What we'll see the next time through is now's the time to run this function and check the examples, but that's a little counterintuitive right now. So I'm just going to go on to the next step. The next step is something called the template. And what we do in order to write the template is we first comment out the stub. So this was the stub, and it's now commented out, which seems funny, of course, because we never did anything with it. As I said, you'll see in our next run-through of a function design that we do use the stub to do a preliminary check of the examples. For now, I'm commenting out the stub, and I'm writing something called the template, which looks like this. In this case, the body of the template looks just like that. What the template is it's a list of the ingredients that the body of a function has to work with. This is going to show us what we have to work with when we actually finish the function definition. And you should read this as saying, well, the function has a single parameter n, and n is something you have to work with. And the dot dot dots just mean you should do something with n. So that's the template. And now we're almost done. The next step is to code the body. What I'm going to do is make a copy of the template. I'll copy it. I'll paste it here. I'll comment this old version out. And the reason I'm doing this is just in case I mess up down here and I need to go back to the template, I have a copy of it. So now I have the signature, I have the purpose, I have the stub, the examples, the template, and the final step is to finish the function definition. Now here there's a very important point, which is everything that I've written before can help me in figuring out what to replace these dots with. The signature tells me that n will always be a number. The signature also tells me that this function must produce a number. The purpose tells me that it's a number that's twice the given number. And the examples give me concrete examples of that. And the template's showing me, reminding me what I have to work with. And now using all that information, I can write times 2 here, because I know that I'm supposed to multiply n by 2 to produce the result. And now it seems like I should be done, but the final step is always to run the function and make sure that it works properly. And here's where you're going to see what check expect, why check expect was so helpful. If I click on run now, Dr. Racket will tell me that both tests passed. What that means is it called times 2 with 3 and made sure that the result was 6. And it called times 2 with 5 and made sure the result was 10. And so in this case, both tests pass. In a future video, we'll see that sometimes your tests don't pass, and then you have to go back and debug the function and/or the tests. So that's a very quick run-through of the how to design functions recipe. Remember what I said at the beginning. That run-through is too quick for you to fully absorb the design recipe. We don't intend you to fully absorb it from that quick run-through. Instead, the purpose of this quick run-through was to give you an overview of how the recipe works. What I recommend you do now is perhaps view the video again, and then go to the course website, look at the How to Design Functions recipe here, and work through the website's version of it, which is a bit more detailed. And then in lecture, we'll do a number of other examples using the How to Design Functions recipe. And we'll talk about things like using the stub to do a preliminary check of the examples, what to do when there's errors, how to write more elaborate examples that can help you with designing more complicated functions, and lots of other issues.